Welcome to example 6. We have two bodies that are connected by a light cord to this pulley. And this block, this rectangular block, is on an inclined plane that is frictionless. So we're told that the hanging weight is 10 kilograms. So we'll just label that M1, and M1 is 10 kilograms over here. The block that is sliding along this smooth inclined plane, we'll label that as M2, and we're told that mass is 5 kilograms. We're told that this is a nice smooth incline, which means that it is frictionless, and we'll get into friction later on in the next class or two. The angle of inclination is not shown in the diagram. I should have shown that. This is angle theta. So this is the angle with respect to the horizon, and that angle is 30 degrees. We also know the acceleration due to gravity is 9.8 meters per second squared. So we start our problem by first drawing separate free body diagrams for each of the two bodies that are connected by a pulley. So go ahead and stop the video here for a moment and take a minute and draw the forces, the external forces that are acting on M1 and all the external forces that are acting on M2. Label all your forces and then check them. Okay, so M1 should have a force that is acting downwards. This is the weight of the block pulling down. I'm going to label that as F sub G1, which is the weight of the block, which is also equivalent to the mass times the acceleration due to gravity, m1 times g. Also, pulling upwards on the block is a tension. And we'll label that force as F sub T for the force of tension. Okay, now next going on to M2. What forces are acting on that body? M2 has a weight pulling down, which we'll label as F sub G2, which is equivalent to the mass of that body times the acceleration due to gravity. We also have the tension pulling upwards on the rope, pulling on the block, so along the direction of the rope. And because this pulley is frictionless, you can assume that the tension that pulls on this block upwards is the same as the tension that pulls upwards on this hanging weight. So these two tensions are the same. And lastly, we have the support force, or the normal force, that acts perpendicular to the surface. And I will label that as F sub n for the normal force. You could label that as also just n. You could also label these simply as just T, capital T. Okay, so once the free body diagrams are drawn for the two separate bodies, we can then define a coordinate axis for each object. And you're at the liberty, by the way, of choosing your axes to orient differently for both bodies. You don't have to have the same axes for this body as you do for M2. They can be changed around or tilted, for example, over here. So let's start with this body. You have, it looks like, and one other thing, I guess, before we even draw out the axes, I'd like to indicate the direction that the system is moving. You're asked to find the acceleration of the two masses, so we must assume that maybe the system is being released from rest and then accelerating. Either this block is sliding up the inclined plane or the block is sliding down the inclined plane. Now you just have to take an educated guess where you think it might be sliding. So you could assume this goes down, and if this goes down like that, then this block would be going upwards with the same acceleration because they're all connected together. So the acceleration of the block going downwards is the same as the acceleration of this hanging weight going upwards. Now if, for example, the acceleration is not really going down the ramp and up here for the hanging weight, and it is going in the reverse direction, then that's fine. You can still solve it. It's just that the only difference is that when you calculate your acceleration, your answer is going to be negative. It'll be the same magnitude. It'll be negative because you chose the incorrect direction in your diagram. Okay, well, let's just stick with this and see what happens. So we need to choose a convenient coordinate system for here and here. So let's start off with this hanging weight, and we can assume that, I suppose, that going upwards, you can draw a little axis up here, is going to be positive. Sometimes we just simply draw this a little bit on the side here and make it y. And so the person who's grading your paper will know that you're assuming upward forces are positive and downward forces are negative. Next, let's take a look at this body over here. In this particular case, it's accelerating down the ramp. So I would think it would be convenient to choose your x-axis along the direction of the acceleration, and then the y-axis perpendicular to that. You'll see that the normal force is right along the y-axis, and the tension is along the negative x-axis, and the weight is along, well, it's actually at an angle, so you're going to really have to break that up into components later on. I believe I mentioned this earlier. The tension here and the tension here are identical in magnitude. The only difference that's occurring here is the direction. This will be pulling this block up along the inclined plane, and this will be pulling the hanging weight upwards straight up vertically. But because this pulley is frictionless and massless, we can say that they will have exactly the same magnitude. Okay, so we're now ready to proceed on to solving for our acceleration and our tension, which are two unknowns. So let's take a look at one of the bodies. Let's do the hanging weight first. Okay, so if we look at these two forces, one of the forces has to be bigger than the other force because this body is accelerating upwards. And so I've drawn purposely the tension a little bit bigger than the weight because this force is larger. There's more upward force than downward force. We're making that assumption so that you get a net force that is acting upwards. Because the body is accelerating, we can say that the sum of the forces along, well, our y-axis is equal to the mass times acceleration. That means when you add these forces, they will give you a result of mass times acceleration. Now you want to be careful. There are two different masses and they have different masses. So we're going to label that as m1 because we're only dealing with that particular weight. Okay? So now this means add all the forces along our y-axis. Now, because we assume that y is positive upwards, the tension is going to be positive, but the weight is going down, so that will be a negative. So you're really doing something like this. This means add all the forces. So we have tension up, that's one force, that's positive. And then we have the weight. You can do it like plus, because you're simply really adding them. But then we take care of the direction by putting a sign in front of this. So we don't have negative 9.8 as you notice here. We take care of that negative by putting it in front of the expression. So we're going to write minus Fg1 equals the net force, which is m1 times a. Now you could probably just rewrite this as Ft minus m1g, because that's what the weight is equal to, the mass times acceleration due to gravity. And this gives you a net force of mass times acceleration. If you look at this question carefully now at this point, you can see that the acceleration is an unknown and the tension is unknown. However, the mass and the acceleration due to gravity are all known. So that means you have an equation with two unknowns. Now, if you'd like, you could substitute numbers in, but I would like you to get into the habit of solving things symbolically, because on the AP exam, you're going to have questions where you have to solve it all symbolically and then just do your substitutions at the end with numbers if they're asked. So let's try to practice solving this problem just algebraically, just with symbols, and the very last step we'll put in the masses and the angles and so forth. Okay, so since we have one equation with two unknowns, we need to get another equation, something that involves a tension and something that involves an acceleration. So well, we're done with this hanging weight. We now need to be moving over here to the block that's sliding along the smooth inclined plane. Now, if you look along our y-axis, we have a normal force, and then we have a weight that's partially in the x and the y. And then along the x-axis, we have the tension, and again, we have a weight that's partially in the x and the y direction. So we need to take this weight and break it up into components. Okay, so let's go ahead and do that before we proceed on to applying Newton's first law or Newton's second law. So this force of gravity needs to be broken up into two components. There's a component that's going this direction. That is the perpendicular component of the weight to the plane. And then we have a part of that weight going along parallel to the plane. I like to label this as F sub gx along our chosen x-axis, and then F sub gy for along our y-axis. So we're going to now replace this weight with these two components. Now, to get your angle properly done, make sure you're using the right trig ratio. I highly recommend that you redraw this out as a triangle below in a separate picture. So I'm redrawing this over here, just made it a little bit larger so we can see it. This is the weight, which is equal to m2 times g. This is weight 2, really. And now we're going to show the y component of that. Here's the y component, fgy. And we're going to take the x component here and put it over here now so that we can make a triangle. We'll do it over here now. And this is the x component of that weight. And the x component and the y component are always perpendicular, so this is your right angle right in here. And well, you know the mass and g, so you really know the hypotenuse of this triangle. But we want to rewrite this and find out what the x component is and the y component is in terms of the weight and some angle. Now, theta here is given as 30 degrees. This is a 90-degree angle. If this is 30 degrees, then up here this would be 60, or 90 minus theta. Because remember, all the angles in a triangle add up to 180. Now, if I were to draw a parallel line along our y-axis and just shift it over here to the top of our triangle right here, which is there, hopefully you'll see that this angle right in here is the same as this angle in here, which is also the same as this angle right over here. And you know that this dashed line in red that I've drawn is parallel to the y-axis, and that is perpendicular to the plane. And if this is 90 minus theta, that means this must be theta. Right? This is 30 degrees. This must be 60. And 90 minus 60 makes this back to 30. So therefore, their angle right here with respect to our weight and the y component, that is the angle that is 30 degrees. Hopefully you can follow that. If you ever really just get stuck trying to figure this out, you know, you can just make your triangle like a little sliver and then draw it out, and you can easily see, oh, that angle is the same as that angle. Okay, so now if we know the angle and this part, the hypotenuse, then we can rewrite the FGX in terms of this and the angles. What trig ratio would you use that involves this side, which is opposite of that angle, and the hypotenuse? Hopefully you're thinking sine theta is opposite over hypotenuse, which is m2 times g. So our x component of the weight for this body is equal to m2 times g times sine of theta, or 30 degrees. We'll leave it all symbolically right now. So now, if we move along our x-axis, we'll come back to the y in a moment. If we come along the x-axis here, let's now apply Newton's laws. Now you see, you imagine that you've replaced this force with these two forces, and we're looking at this x component of this weight, which looks tinier than that, not obviously realistic. This probably should have been drawn a lot bigger. It looks like Fg2x is causing it to accelerate to the right, but then the tension is pulling back. So the combination of these two forces is causing this block to slide down along our x-axis. So because the block is accelerating along our incline, we can write the sum of the forces along the x-axis equals ma. Now remember, be careful to use appropriate subscripts because we're talking about mass 2, not mass 1, not the combined mass, but mass 2 only, because we're just looking at that body accelerating. So we'll rewrite the right side just as m2a. That's what the net force is equivalent to. And this means add all the forces along the x-axis. Forces that go in the direction of the acceleration here along our x-axis are positive. So Fgx is positive. But our tension, which we're adding, is actually negative. You can probably just rewrite this as m2g sine theta. We're replacing the x component of the weight with that, minus the tension equals m2 times a. Now, looking at this, you see that you know the mass, you know g, you know sine of the angle is 30 degrees, and you don't know the tension, you don't know the acceleration. So you have a second equation with the same two unknowns. And so now the problem becomes a solving simultaneous equations problem. You need to eliminate one of the variables. I think the easier variable to look at this and eliminate would be the tension, just because it's all by itself. So I'm going to take this equation and take one more step, put tension all by itself. So it'll be m1a plus m2g. All right, not m2g, actually m1g. I'll just erase that. m1g. And then now we're going to substitute this equation over into number 2. So we're going to sub 1 into equation 2, which is shown here. So we have m2g sine theta minus m1a plus m1g, and that is equal to m2 times a. Now let's get rid of the brackets, and you get a negative m1a and a negative m1g when you get rid of the brackets. And the unknown of a here and a here, you need to combine like terms. Everything else is known. So let's get everything onto one side. Let's put it on the right side, and we'll combine like terms. So we have an a here, we'll pull, and I pulled out a g since that's in both of those terms. And then rewriting a by itself, you get this expression. And now at this point, you can simply just substitute your numbers in. And we get the following expression. And then when you solve this, you get an answer of negative 4.9 meters per second squared. Oh, I got a negative here. So what did that mean? Well, it means that in my diagram, I chose the wrong acceleration. I thought this body was going to accelerate upwards. How silly. This is 10 kilos. This is only 5 kilos. Actually, the system is accelerating the other way. But notice I got the same answer. It's just the only difference is it's accelerating down the ramp. Or sorry, up the ramp, and the hanging weight is going down. So does it mean that I have to repeat the whole problem because of this minus sign? No. It just means that the block is accelerating in the opposite direction as defined. So it's accelerating up the ramp. And I actually purposely did that in this problem to show you would get the same numerical answer, except you just have a negative. Okay, now using that negative answer, you do not need to make it positive. Leave it as negative because this is the way you've defined it. Now find the tension. And you can use any of the equations. You could use equation 1 or equation 2. It really doesn't matter. I'm going to use equation 1. So equation 1 states that the tension is equal to m1a plus m1g. So the tension is equal to the mass 1, which is 10 kilograms, times the acceleration of negative 4.9 meters per second squared, plus another 10 kilograms times 9.8. So this gets you an answer of a tension of 49 newtons. All right, so our acceleration has a magnitude of 4.9. You can neglect the negative when we're giving the answer and just say what direction it's actually going. And then the tension is 49 newtons. Okay, and that's it for this example.